So welcome everyone. We are delighted to have Professor Krishna with us for the second distinguished lecture as a part of the degree program. Krishna is a professor in the CS department at IIT Bombay. Her research interests are broadly in theory with a focus on logic, automata, and problem verification. And today she is here to tell us about verification of concurrent programs.
Thank you, Mrinal and Ramprasad, for the invitation. So this talk is going to be very different from what you've been doing so far. Okay, it's a very different kind of stuff. Not so much math, I would say. Okay. And this is supposed to be an overview talk. So I'm just going to talk about the area called verification of formal methods. I don't know if you have heard about it in your undergrad studies. So that's what I'm going to talk about, with a focus on so-called concurrent programs. The weak memory, we'll see what it is. Okay, right now, just verification, concurrent programs. Let's focus on that first. Eventually, we'll get to know what is meant by weak memory. So even before I start, just a bit of motivation. I always have this first slide for concurrency, just to motivate concurrency. So the simple motivation for concurrency is that I'm going to claim concurrency is everywhere. Okay, now why is that so? Is it true? So if you look at, let's say, the lowest level of system design, right? Level of chips, right? Every machine you think of is multi-core, right? We no longer have single core machines. And in fact, what I'm saying is supported by, if you look at all the machines from Intel or IBM Power or ARM, they're all invariably multi-core machines, right? So at least at the lowest level, at chip level, there seems to be concurrency in action in terms of multiple processors working together. But now, actually, if you look at the highest level of system design, okay, it's what we call distributed databases or geo-replicated computing. There, again, you can see that there's concurrency. A simple example, right? So if you think of Facebook, right? If I like the photo a friend has posted, suddenly everybody who is also connected to that friend sees my like, right? So it's basically something is going on at the back end so that, there is a proper view for everybody. So it's a lot of concurrency going on at the back end. And now, basically, because of all this, concurrency at the chip level, at the distributed databases level, if you look at the design of modern programming languages, okay, like C20, Java, they've also incorporated, concurrent features in their language. So if you know the language somewhat, if you have seen things like locks, right, release writes, acquire reads, okay, these are all basically concurrency primitives which have been incorporated in the programming languages. Okay, I guess so far is good enough to say that concurrency matters and concurrent systems are everywhere, and somehow it's important for us to verify concurrent systems. So having said that, I think I'll move ahead with the popular notion of concurrency that all of us know is what is called sequential consistency. That's a name attached to it. And this has been around for a very long time, propagated by Lamport in his seminal paper. So what I'm going to do, I'm going to take 3 examples of programs, and we will see what happens if we interpret them under sequential consistency. This is something all of us know. And then I'll move away from that and say, okay, now what happens if I interpret it under so-called weak memory? At that time, we'll see what I mean by a weak memory, so that we see the difference between interpreting it under sequential consistency and under those memory models. And then we will ask, okay, now how hard or easy it is to verify these programs under these modern weak memory models, okay? So even before I look at the examples, I just want to set the notation clear. So when I say I have a concurrent program, what I mean is something like this. Okay, so this is an example of a concurrent program. So TH1, TH2 are called processors or threads. I interchangeably use the terms process and thread respectively. Now, this X and Y that you see here are what are called shared variables. Okay, A and B are local variables. So A is a local variable that's, kind of only this thread is aware of A, only this thread is aware of B, but X is shared by both the processes here. And this operation here is a write operation. So I'm writing a value into the shared variable X. And this one below is what is called a read operation. So I'm reading from a shared variable X into my local variable B, respectively here into my local variable A. Now, given such a program, what I mean by an execution is you basically run your threads in any order, you interleave them and run them. The only thing you must remember is, okay, so here, for example, I've started running this blue thread. There's no compulsion that I have to do it, like this completely. I could have just stopped here and then gone to this. So anytime you stop execution at a particular instruction of a thread, when you come back to it, come back to where you left it off, right? That's the only rule. And then, so this is a sample execution, for example. So as I said, you execute instructions of any thread in what we call program order. So program order is the order in which the instructions appear in the respective process or thread. You interleave it as you wish. And then the standard rule under sequential consistency is that you always read from the last value written, which is what we are all used to, right? So in this example, suppose I wrote xs1 followed by xs2, and then if I try to read, they both will read the to value 2, right? Because that's the last value written. So in some sense, in the memory, there is just one value for every shared variable. And that is what sequential consistency is about. And given such a program, now I may want to ask, is it possible for this assertion to be true? So what I mean is, if I execute this program, can I reach this assertion, which means can I see A being 1 and B being 2? Okay, this is the kind of assertion I'm trying to ask. Okay, assertions can be more complicated than this one, but this is just a sample assertion. So now we start the examples. Okay, so all my examples are what are called litmus tests. So litmus tests are standard benchmarks, which are kind of used to test if a certain model works as it is supposed to work. Okay, so the results are kind of known and you map what you get with, what is expected. So here, let me ask you, so in this program, again, I have two threads, two processes, whatever it is. X is a shared variable, Y is a shared variable. Rx is a local variable, right? So to begin with, I'm assuming that both the shared variables are value 0. I want to ask whether you can, attain this assertion. Can Rx be 0 when I finish executing my program? So notice that I'm reading into Rx only here, right? To begin with, Rx is kind of undefined. Like the shared variables are value 0. So maybe we can see what happens when I proceed with an execution. So notice that when the first instruction got executed, the value 1 is immediately reflected in the global memory. Y is still 0 because no write has happened to Y so far. So now the second thread is trying to read, okay? So it can read 0. So as long as it reads 0, it's going to stay in the loop, right? Because it can't proceed. Now at some point when the first thread executes the instruction write to Y, now the global memory is updated, so X is 1, Y is 2. So at this point, now it can come out of the loop, and now it's trying to read from X. So obviously, when it reads from X, the value it's going to read should be 1. So which basically means that this specification does not hold good under this particular program, right? So when I say does not hold good, what I mean is, now this is one sample execution, what I showed you here. So when I say does not hold good, what I mean is, try to execute this program under any possible way, right? No execution of this program under sequential consistency can give you Rx is 0, which means this is not possible under this program, right? So so yes, this is not possible. So now I move on to my second example, which is called a store buffer. So once again, two threads, two shared variables. I also have two local variables here, that is Rx and Ry respectively. To begin, they're both 0. And I'm asking, can I attain Rx and Ry to be both 0? Okay. So let's see. So I'm writing 1. So the global memory is updated. So now if that guy tries to read from X, it indeed can read 0. So Rx 0 is possible, of course. And now I'm trying to execute the first thread. So the global memory is updated. But now when that guy tries to read from Y, it cannot read 0. Right? But this is one sample execution, what I've showed you here. Under this sample execution, I'm not able to attain both Rx and Ry 0. But then I would like to ask you, there are, of course, other possible executions, right? With different interleavings. Do you think there is an execution where you can actually get Rx and Ry to be both 0 or not? It doesn't look like, right? Okay, so indeed, yeah, it's not possible under sequential consistency. I cannot get both Rx, Ry to be 0. So let's move on to my last and third example. So there's yet another litmus test called 2 plus 2W. The names are not my choice, okay? They are standard names. I'm just lifting them here. Okay, it basically says 2 threads, 2 writes. Okay, that's what it means. So let's see, I have again 2 shared variables, X and Y. There's a local register A, local register B. Can I attain A is 1 and B is 1? I don't remember if I have the execution here, but maybe we don't need it. So what do you think? Can I attain it or I will not be able to get it? Okay, since I want to read 1 into A, let me try writing y equal to 1 first. But then by the time I try to read from y, this guy would have written and overwritten the y equal to 1, right? So it's not going to help me. Likewise, if I try to see, okay, can I read this one? The same problem, right? Even if I start with here, by the time I come here, this would be overwritten. So I don't think this can be possible under sequential consistency. So yes, it's indeed not possible. Okay. So I'm done with my examples for the basic model, sequential consistency. So there are several good things about sequential consistency, right? It's very easy to understand the program because it's a very straightforward semantics. So for the programmer side, it's very easy to write a program, interpret it under sequential consistency. But if you think from, let's say, from a performance point of view, right? If I try to have a machine whose underlying memory model, as it is called, is sequential consistency, there is a lot of back and forth happening, right? Every time a write happens, it's immediately reflected in the main memory. So this is something that's not very good for performance issues, right? So this is why the modern architectures do not implement sequential consistency. So in some sense, what they try to do is, okay, can I not, ensure this continuous traffic from the process write to the main memory? In some sense, I want to kind of make it a bit more relaxed. So you put to the main memory only on a need basis, let's say, which means, this is not compulsory that you lead from the last value written. So that is the kind of motto of the what I'm going to call weak memory models. So I'm going to talk about 2 weak memory models, and I will conveniently drop one of them in the later part of the talk and try to focus just on one of them when I talk about the verification part. So the weak memory model, the first one I'm going to talk about is called total store order, TSO for short. And who implements TSO? So first of all, right, the seminal paper which introduced this is a paper from Sevel et al. It's a POPL paper. So POPL is flagship conference in programming languages, okay? Principles of programming languages, POPL, POPL, that's a short form. And then if you look at the Intel architectures are basically implementing TSO. The Spark architectures also kind of are a bit like TSO. Okay, so that is the motivation, the practical setting that TSO has, these practical advantages. And TSO is actually weaker than sequential consistency. So we will see how it is weaker. I'm going to run the 3 same examples and we will ask, okay, what happens if I interpret the same program under TSO? Do the specifications still continue not holding good, or does TSO allow, actually witnessing some of those specifications? Okay, this is what we'll try to understand. So the same message passing example. So now I should explain what these blocks are. So the same program, the same 2 processors, the same main memory, except now between every process and the main memory, I have a buffer, a queue, okay? A first in, first out queue. So that is what is there between a process and the main memory. Now we'll exactly see how this queue is used by actually running the program. Okay, that's, I think, the best way to understand how the queues are used and what TSO looks like and how it differs from sequential consistency. Okay, so now let's start executing. So when the first guy writes x1, so what happens whenever a process writes to a shared variable? Notice that it is not reflected in the main memory, but it is stored in the buffer of the process who made the write. Okay, so that is the first thing. Which means now if this guy wants to read from y or even from x, okay, maybe I should execute it a bit more before I start talking. Yes. So now this guy is written to y also. Okay, so now notice that again the main memory is unchanged. Okay, now the buffer ordering is followed. So the writes are stored in the buffer in the order they are kind of written by the actual process. So now if this guy tries to read from y, what it will do is it will try to look at its own buffer. Okay, it will see, have I written to y before? If I have written to y before, that is what this guy will immediately read. So in this case, this guy has written nothing to y, which means its point of reference is the global memory. So it will read only y equal to 0 because it is not seeing that the fact that this guy has written to y because it's hidden in this guy's buffer. And this buffer is not visible to this guy. Okay, so at this point, it's going to stay there. Now, at some point, I can non-deterministically flush my buffer. So this is a completely non-deterministic operation. So it can so happen that, as soon as something is written, it can be immediately flushed to the memory. That's a possibility. If that happens, it's exactly like sequential consistency, right? Because everything is immediately updated. So the buffer is not really used at all. That's one possibility. The other possibility is that, I write a lot of things in my buffer and I put all of them together in the memory, or I can do it as I feel like. Okay, so in this particular execution, I've just flushed the first guy into the memory. So X is 1. So now if this guy again tries to read Y, well, it still sees 0. It's going to be stuck there. Eventually, at some point, when that flush happens, now the memory is changed. And now when this guy tries to read from Y, okay, now it will see a value which is not 0, so it can proceed with the execution. So now it's going to continue. Now if it tries to read from X, so once again, because it does not see any write to X in its own buffer, it's going to look at the global memory. It will read X is 1. And this specification is not met. But this is my sample execution. So do you think, so I hope the TSO semantics is clear now, right? Any write in the local buffer flushes from the buffer to the memory, non-deterministic. When I try to read, I try to look at my own buffer. There's only one thing that this example does not convey about TSO semantics, which is, suppose this was also X is 2. Okay, suppose I made 2 writes to X, let's say. The buffer will look no different. So it will be, the first write and the second write. But now if I had a read from X here, it will read the latest value written to X, which is what this example is not conveying, but otherwise nothing changes. So now, do you think that even if you think of a different execution other than the one I said, do you think Rx equal to 0 is going to happen? No. Okay. So that's true. I still can't see an execution with Rx being 0, which means on this particular example, TSO and sequential consistency are behaving exactly in the same manner. Okay, TSO does not have any extra executions where I can see Rx is 0. Yep.
There's no bound on how large the buffer can be, or
good question. Good question. Yeah. So theoretically, there's no bound. But when I try to implement it in my Intel machine, obviously it's a bounded buffer. Yeah. So if I want to talk about, the complexity of the reachability problem, I will assume the buffer is unbounded. But certainly when you look at a machine implementing TSO, that's not true.
I can't make any guarantees that because my buffer is small, it won't get flushed away.
No.
The flushing process is not in my control.
Exactly. So yeah, so the operational semantics allows the buffer to be unboundedly big. Yeah. And yeah, you don't have to flush. That's true. Okay, so the store buffer example now, let's see what happens. Okay, so this guy wrote Y is 1. This guy wrote X is 1. Now both people are trying to read. So now tell me, what do you think will happen? A bit louder. It will read from the global memory. Exactly. Now this guy has not written to Y. So it consults its buffer. It does not see a write on Y. So it is free to read Y is 0. Likewise, this guy is free to read X is 0, which means it is actually going to witness Rx is 0 and Ry is 0. So there exists an execution where the specification is actually going to be met. Now, this is an extra behavior which sequential consistency did not give you. So this is what we call a weak behavior. Weak in the sense, normally when I say weak, so sequential consistency is a very strong memory model. So as you become weaker and weaker, you allow more and more behaviors, okay? That is the meaning of the term weak. Sorry?
So they can read the global variables only, and those particular variables are not present.
Exactly. Yeah. So if you want to read from the global memory, yes, your buffer must not have a write on that particular variable. Yes, that is the only thing. Exactly.
At some point of time, I'm expecting that there will be inconsistency. Let's say I'm not updating my global memory, and somehow the other process, whatever is in the global memory, that will a lot of computation, and we do a lot of computation, and we get some value which is not the actual value that the previous process is done. The value. So the previous process changed the value after the second process has done a lot of input.
That can happen.
This other guy has to use that again and all the operations. So wouldn't be like more, will take it more time?
So see, really speaking, right, there is no talk going on between the two processes, right? There's no talk. So literally, if I want to read something that the other guy has written, my only hope is that it gets updated in the main memory. That's all. So there's no other hope. So yeah, you are right in the sense that this guy could have written, let's say, several values to y. This can actually happen. And it's also possible that, some of them are kind of updated here. And if this guy has never written to y, it's going to read a value which is certainly not the last value written. That's definitely going to happen. Another possibility that can happen is that if there are multiple values written to y, okay, even if there's a loop here, let's say, which is reading from y, it's not necessary that, all the writes written will be read, right? Because every time I flush, it's like I've lost that value because it can get overwritten, right? Sure. Yeah. So what you're saying is, if I want to verify whether a program written in TSO behaves as expected, it's not going to be easy. I agree with you. I mean, that was what I was trying to say also. So if somebody is interested in the theoretical result behind this, right? If you want to kind of translate what will be the complexity of the reachability, okay? When I say reachability, you understand what I mean? So reachability means, can this program reach a point, a configuration where it witnesses this assertion? Okay, that is what I mean by the reachability problem. If you want to understand the complexity of that, or if you want to ask if it is decidable, you know what is meant by decidable, undecidable, right? So this problem is actually decidable for TSO, okay? And the proof basically is by simulating this with what is called a lossy channel machine. Okay, there is something called a lossy channel machine. It's basically an automaton with channels, okay, or a network of automaton channels connected between them. Now, this complexity is like very bad. Okay, the lossy channel machine complexity is like Ackermann hard or non-primitive recursive, if you know non-primitive recursive. So it's like, just below the undecidability barrier. It's like, the worst kind of decidable thing you can get. So it is decidable, but it's like super bad. Okay, that is the complexity of the TSO reachability problem. If you want to read up, I can suggest references at the end of the talk. As I said, this talk is supposed to be super light. It's just going to tell you, okay, there is this model, there is this model, there is this problem. And, this is how we go about it. Okay, I'm not going to go into any theoretical stuff, but if you think there's something you would like to do, I can suggest references. All right, so my last example, which is 2 plus 2W again under TSO. So what do you think? Okay, so X is 1, Y is 1, okay. The second write and the second write. So now let's see. So if that guy wants to read 1, so notice that this guy wants to read 1, that value is available here. So maybe if I flush the buffer, just part of the buffer here at this point of time, which I can completely do, then if this guy tries to read, would it work? No, because this guy has its own write, so it's compelled to read that. But hold on. So what if I flush this entire buffer and then try to read? Would it help? So you're saying if I try to help one person, I'm hurting the other person, right? So it doesn't look like, I can achieve both A and B to be 1, right? So it's like, the cross read kind of thing, right? I want to read like this, and that doesn't seem to be working here. Yeah, again, I don't have all the executions here and all the possible ways of flushing, but by a simple check, you can convince yourself that no, it's not going to happen. Okay, so I'm done with TSO. So now, out of the 3 examples we saw, TSO is basically relaxed in 1 example out of the 3. Right? The previous example, it gave you what sequential consistency could not give you. And here again, well, even though it has extra behaviors, it's not going to still enabling this specification. There does not exist an execution where you can see this particular specification being satisfied. Okay, I'm done with TSO. I'm going to my third memory model. Now, this is the memory model which is kind of coming from the programming languages perspective. Okay, so this model is called release acquire. So this is the paper which kind of, what do you say, introduce the semantics of release acquire. So it's a fragment of RC11, okay, because it was POPL 2011. Now there's RC20++. Okay, but anyway, so this memory model is what I'm going to talk about now. So we'll see what I mean by release and acquire once we see the example. So again, I don't have the proper operational semantics here. So what I'm having is like a lightweight thing, trying to convey what I mean by array. Hopefully it will be clear. All right, so same example, message passing. So let's see. So the one main difference that release acquire has compared to all the others is, so here in some sense, if I try to read a value, right, I can either read what I know currently, or if you come and tell me about something, right, if you have communicated to me that, hey, you know, there is this value which was written, then I can read that. Okay, this is like the high level definition of array, but maybe at the end of this, it will become clearer. So I have, you know, a timeline here. So P1, P2 are the two processes I have with me. I have two variables, X and Y. Okay, to begin, what this picture depicts is that the knowledge P1 and P2 have about what is written to X and Y is at the beginning. Okay, which means they don't know of any updates to X and Y. They both only know that X and Y have an initial value called 0. That is what this picture depicts now. And as I keep writing, I'm going to, you know, make these guys move in the timeline. So it's literally a timeline. Okay. And then we will see what happens when somebody reads something. Okay. How is the information passed? Hopefully things will become clear. So when the process 1 wrote to X, okay, it updated itself from its initial knowledge of X to a higher knowledge of X. Okay. That is what this shows. It has moved to anywhere from the starting point. I mean, this is just any point, okay? I could have just moved right here, or I could have gone all the way there, okay? It doesn't mean anything. It just means, you know, upgrade from where you stand. That's all it means. Now it's going to write to Y, which means, okay, P1 has also upgraded, you know, itself from its initial knowledge of Y to something higher. Notice that these two are not the same point, okay? They could be the same point, but all I wanted to say is that, okay, from the initial knowledge, they've moved ahead. Now, what does P2 know about X and Y? It is unaware of the writes made by P1 to X and Y. Okay, that is what this picture is trying to say. It knows about the initial value. Okay. Okay, you can imagine that, you know, there is a world out there where these writes are published. So that is the scenario. So it is aware of what it knows currently, which is the initial values. And there is a world out there where these values are published. So now the interesting thing is what happens when it tries to read from Y, read from X. So let's see. So now at the while loop, can P2 read the value 0 from Y? Its knowledge about, you know, Y is at the beginning. It knows Y is 0 was the initial value. Okay, there is a world out there which tells, okay, a write to Y happened, but it's like I have to open the window and look out. I was sleeping, I continue to sleep. So it can continue reading 0. It can continue telling itself, hey, Y was 0, Y was 0, right? Which means it can stay in the loop as long as it wishes. However, there is a possibility to wake up and look out and look at a higher knowledge of Y out there and upgrade yourself. Okay. Now, so let's see what happens when it finally opens the window. So when it opens the window, notice that it catches up immediately with everything. What do I mean by everything? So there is basically some causality at play here, okay? So when it realized about the write made to Y, the write was made to Y after the write to X was made by P1. So when it learns about this write, it learns about that write also. Does that make sense? It's like in chronological order, right? So this is also why, you know, the term release and acquire kind of makes sense. So this guy has now acquired knowledge about what happened here. And this guy has released its knowledge. Okay. So this arrow, later we'll see, I call it reads from. Okay. So the reads from basically is the only way to communicate in release acquire. So it's like a handshake. You come and tell me everything you know. And then once I learned everything, that somebody has told me, I cannot degrade myself, which means when I try to read from X now, notice that where does P2 stand? Oops. P2 is standing here, right? Now P2 cannot read the initial value of X because it has gone beyond that. It cannot degrade itself and read an obsolete value of X, which means under release acquire, I will not be able to see Rx equal to 0. This example is fine? All right. Okay.
Why is equal to X equal to other?
If it was X is equal to 0, I see. Yes, perfect. Yeah. So what you're basically saying is, if the while loop was saying while X is 0, and if it chose to open the window and read this value of X, basically what you're saying is that P2 would progress with P1 only on X, but not on Y. Good point. Does everyone agree on that? Which is like, okay, there is this information followed by this information, but if I choose to read only up to this point, I can still sleep with respect to the variable Y. Yeah? Yeah, so what she asked is, suppose here I said while X is equal to 0, which means if P2 is trying to read from X, then what she's saying is, so now, if you remember what happened when it read Y2, right? P2 suddenly progressed, to P1's view of both X and Y. So her point was that if it was reading from X, then P2's knowledge only can be up to date with respect to X. P2 can still pretend to not know about Y, which is fine, which is basically causality, nothing else. So it's like if you know a later event, you know the earlier event.
To an intermediate state of process one's knowledge.
Exactly. Depending on, where it is reading from. Exactly. Yeah, great point. So in some sense, right, if there's a big amount of knowledge, if you choose to read from here, you know everything from there till here, but not necessarily the ones below, because it was not conveyed to you. It is there, it is out there in the world, but you have not upgraded yourself because, it's like immediately when you give me, I become enlightened. And okay, if necessary, I can continue with this current level of enlightenment, or I can continue to read more and more further values. Yeah.
Go to some intermediate point. You don't have to see everything written out there.
Exactly.
Find that there are just 2 processes. Suppose there are 3 processes happening.
Yeah.
What does it mean for an intermediate stage?
So it depends on who you want to read from, right?
You just go to a point which maintains some monotonicity or something.
Exactly. It is monotonicity, causality, whatever we may want to call it. Pretty much. Yeah. Exactly. So, at least, right, when this arrow kicks in, so, okay, if, as somebody else asked, right, if the arrow was here, if it was X is equal to 0, right, if it chooses to read from here, notice that what is passed by means of the reads from is only everything above up to this point to here, right? Now, because it reads this, everything above is passed and, causally conveyed, pretty much. Are we good? Okay. This is not such a hard example to see. So I would like you to tell me, do you think Rx and Ry0 is possible or not? Let's see. So the first process, okay, second guy wrote Y. Okay, it upgraded itself from the initial knowledge of Y. First guy upgrades itself from the initial value of X. Now this guy is trying to read from Y. Yes, out there in the big world, there is a knowledge of somebody wrote to Y. It can choose not to read it because nobody has come and given it that particular knowledge. It can also choose to upgrade, right? So at this point, there are 2 possible values that Ry can read from. It can continue to be happy with what it knows at this point of time, which means it can read 0. There's no contradiction there. Or it can say, hey, somebody wrote to Y, let me go and upgrade myself. But the long and short of it is that there is a possibility that Ry can be 0. There is an execution where Ry can read 0. Likewise, there is an execution where Rx can read 0. Make sense? Yep.
Are these both are probabilistic that sense, like how do they decide what to take? Is that random?
Right now, there is no probability attached to what I'm talking. Right now, it's just non-determinism. But you can imagine a probabilistic semantics for RA. Absolutely. So even for TSO, right? Actually, because you brought the probability. For TSO also, right? Like as Ramprasad was asking about the buffer size. You can definitely attach a probability notion there also, okay? To say that the buffer must be flushed, more and more and more. You can attach that notion to, and there exists something called probabilistic TSO, probabilistic RA, but I'm not going there right now. Was there a question? Okay. Yep. Completely random. I mean, this was just my choice of execution. I mean, I'm just following the program order, right? I mean, I do have to make this and make this before I come to these guys. Yep. I do. Exactly. Yeah. True. But okay, if you want to, appreciate where this differs from sequential consistency, I agree with you. So if I did this and did this, yeah, invariably I would read 0. But then, when I come here, in sequential consistency, I don't have a choice of reading 0. Whereas here I do. Right? That's all. So the point is that, having both 0 was not possible earlier, but now that's possible. That's pretty much it. All good? Okay, the last example and perhaps the most interesting one for RA. So do you think I can read A and B both to be 1? Okay, yeah, I can show the timeline. I don't know if it will help much. So P1 upgrades itself with respect to this X knowledge. P2 is upgraded with respect to Y. So now what I want to ask you is the following. Okay, now when P1 makes the write to Y, where do you think P1 should jump? Can it jump here, or it doesn't matter? Question is clear, right? P1 is going to make a write to Y. P2 has made a write to Y. It's out there in the world. Now, as far as P1 is concerned, its knowledge of Y is 0. And what we said is anytime I make a write, I go beyond my current knowledge. And my current knowledge is 0, which means it's okay if I jump here. Right? Okay. I'm doing it for a reason, obviously. There is another execution where this guy could have jumped ahead, okay? I am not depicting that execution here. That's all. Likewise, now if I talk about P2 writing to X, okay, P2's knowledge of X is 0. When it makes a write, it has to upgrade itself from the initial knowledge of 0 to a higher one. Once again, P2 can jump here or coincide with P1. It's completely its choice where to jump. It's also jumping like that, so that. Now let's try to read from Y in P1. So what is P1's knowledge of Y? P1's knowledge of Y stands here. Right? So now, okay, can P1 read the value 0 for Y? Everybody agrees it can't. Why? Because 0 is clearly depreciated. By this choice of timeline, P1 has two choices of Y to read from. It can read Y is 1, or it can read Y is 2. We all agree with that? The reason it can read Y is 1 is because that view is even higher than where it has put itself. Right? Similarly, when this guy tries to read from X, it can't read the value 0. That is for sure. But once again, okay, this guy is standing here with respect to X. It can choose to read 2, definitely. That is its own right. But it can open the window and read the value 1 written by this guy. So this is a very non-intuitive example. In the sense, it's exactly this cross-read which is being facilitated by release acquire. By, this interpretation that, okay, my view I can either continue to stay with my view or go to a strictly higher view. The only rule for RA is that don't become obsolete. And notice that all the talk happens here by means of this reading from, right? So the knowledge transfer happens when I read from what is written by somebody. So anytime I read from what is written by somebody, I acquire all their knowledge. They're kind of releasing their knowledge. Okay. No, so it is writing the value 1 to x. So this line is just to say in the causality, you understand causality, right? Causality is like the order or sequence in which events can happen, right? So here, all that I'm saying is take every process, take every variable. When you begin, you have a certain understanding of what x and y are, okay? So this line is trying to say, with respect to the variable x, what does P1 know about x? To begin, it only knew the value 0. Now, when it wrote the value 1, I upgraded it here to tell itself that, okay, 0 is now obsolete for P1. Because it has gone beyond that value 0 to the value 1. But now, when P2, sorry. This is something that happens with Keynote, I'm sorry. So if I have animations, it doesn't let me jump, between animations. But anyway, maybe it's good because you're at that point. Okay, so P1 has kind of jumped from the initial knowledge. And okay, let's ignore y for the moment. Let's only focus on x. Ignore y again. Now when P2 is trying to write to x, right? Observe that P2 is still here with respect to x. In some sense, it has not noticed this write on x. It's out there in the world. But that is why when it tries to write to x, its knowledge about x is it is putting itself here. No, it could have gone ahead. See, I am hiding the formal semantics here. The formal semantics basically attaches something called a timestamp. Okay. If you heard of something called a vector clock, essentially every process maintains a view which is nothing but a vector clock. A vector clock is nothing but a tuple of timestamps, one per variable. Okay. And when a read happens, I have a tuple of timestamps. Okay. There is something in the memory which has a tuple of timestamps. I'm merging the two timestamps. That's basically what happens. When I do the merge, the merge is a component-wise merge where I pick the maximum value. Okay. So which is why, when I try to read from somebody else, I'm acquiring everything that they knew, right? If my view was 0, 0, 0, let's say, at 3 variables. There was a guy who wrote x is 1 followed by y is 1. And okay, if I try to read y is 1, my 0, 0, 0 would become 1, 1, 0. That's basically what I'm trying to explain without going through that terminology. Anyway, this was my new trial. I used to give the formal operational semantics in other talks. It used to become very heavy. So I'm trying to experiment, what is a lighter way of introducing it. There is no buffer here, right? So here every write is in the memory, global memory, with the only extra condition that even though there is everything in the global memory, as a reader, I am not, compelled to read the last value written. I am only compelled to read anything that is above my knowledge, pretty much. Yep.
How can I decide when the program will operate independently and when it will be updated?
You mean when can I read my own write? Or when can I upgrade myself? They are both possible, right? They're two different executions. It's not deterministic. Which is why I'm going to have extra behaviors than at a sequential consistency, right? So every time I make my model weaker, I'm basically seeing one more extra behavior, right? So in some sense, if you think of the possible behaviors under sequential consistency, right? If you have this bunch, under TSO, it's a bigger bunch. Under RA, it's an even bigger bunch. So TSO is weaker than SC and RA is even weaker than TSO. Which is why, as she said, verifying a program under TSO is already hard. Under RA is harder in some sense. Yeah. If P2 passes P1, will it know the, no, it won't. It won't. See, for me to know where you stand, I must talk to you. Which means I must read from something you wrote. Yes, if I am in the initial point, right? I mean, the whole world, I can read anything I want, right? So the only way for me to upgrade my view is by reading from something that somebody else wrote. And at that point, I will know whether you're standing behind me or ahead of me. I won't know that when I make a right myself. When I make a right myself, I only know I stand here, I'm going to jump. At that point, I don't know where you're standing. But if I choose to take something from you, then I will know I'm here, you are there. When I read from you, I jump to your point. With respect to that variable, again. And everything else you have written, if you're ahead of me. Yeah.
What would be actually implying again, these are sort of the guarantees on the chip map, the multiple chip manufacturer that one can, they can say and you want to, is that what's happening here? What is the, what does the software actually
mean?
Yeah.
Okay, good question. So right now, release acquire is, at the programming language level, right? It is trying to mimic the architecture weak memory in a programming language. That is basically what is happening. Having said there is no direct mapping with any existing architecture. It is just the PL community's way of imbibing weak memory into the programming language development. That's pretty much it. TSO. So TSO is what Intel machines implement. Intel x86 actually implements TSO. And yes. So also, right, I have not spoken about memory models like Power, which is IBM's model. They again have a different semantics, which is weaker than sequential consistency. Then we have ARM machines, right? Their semantics also different. I'm not talking about them also. They are more hardware specific. So it's a bit harder for me to talk about them in that sense. Yes, that's right. Yeah, yeah. I mean, these are optimizations which can happen when you compile the code. Exactly.
So for verification of a program, these programs keep running until this specification is satisfied, or like, how does this how do we ensure that this program satisfies the specification, the categories?
Can we take this a bit later? I hopefully will be able to answer you. Okay, I think I will have to go a bit faster now. So this is just a table summarizing the 3 examples we have seen. So this table kind of tells you that array allows the most behaviors, followed by TSO, followed by sequential consistency. Yeah. Yeah.
So kind of I need that from other way. So then I will use like acquire and release so that if I want to know from that one to that, then it can like acquire or release the data.
Yes, see, it depends, right? So the point is, when you look at a program, it looks the same, doesn't matter, right? So if I look at a program, I won't be able to tell you if you're going to interpret it under sequential consistency or array or TSO, right? But indeed, if you're interpreting it under array, then what you said, of course, is going to happen. Every time you make a read, you're going to acquire the knowledge of that guy, and it gets released. Yes. So indeed.
Like without opening the window, I update on my current existing.
On what you've written, on your own rights.
Yes.
Mm-hmm.
I have choice. Is that update on my current knowledge or open the window and update on the.
Of course, it's your choice, right?
Like in my program.
Absolutely. Yeah, yeah. I mean, you can just choose to be in your own shell if you like. Exactly. Depends on the program. Yes, exactly. Okay, so now the verification of concurrent programs. So my question is going to be that, can you check whether there is an execution that witnesses this violation? So I'm okay, assume that there's a violating property, okay? I want to know, does there exist an execution where you can actually see this happen? And how do you do it in practice? No, that is a question. So the input is going to be a program and an assertion. Both of these are the inputs. You have to write an algorithm which will check at the end whether this program has an execution which actually witnesses this bad property or not. This is the verification problem. Now, is it doable? Is it not doable? Is a different question. So for sequential consistency, it's doable, right? It is doable. And the complexity is going to be polynomial space complete, which is not bad. For TSO, I mean, it's not bad because TSO, it's like Ackermann hard. For release acquire, it is undecidable. I'm not going to tell you the proof. Just believe me, it's undecidable. Okay. But now, if it is undecidable, does it mean that we just give up? Or do we do something around it? We should do something around it. Exactly, right? So even for TSO, right? Come on, it's a super big complexity. No, it's not good to work with such a bad complexity. Even there, I have to do something around it, literally. So what we normally do is, we try to work with under approximations, right? So I can try to, think about various semantics which are not the exact behavior, but under approximations are good enough. Okay, good enough to catch bugs, catch violations. Now, there is something called bounded context switching, which is a very well-known under approximation. So what I mean by bounded context switching is, so you all agreed, right, that when I run the program, I can run process 1 for a long time. I can switch to process 2 whenever I feel like. So when I switch, that is a context switch, right? So if I say, give me all those executions with the number of context switches is bounded by 10. Clearly, I'm under approximating, right? I'm leaving away so many behaviors, but maybe that is enough to find my bug. Okay, so there are tools which basically do just bounded context switching. And, many benchmark violations, they can catch with a small number of context switches. That is also kind of documented. Now, this what kind of under approximation is also different, okay? So what most tools do is, if I have a loop in my program, another way I can under approximate is put a loop bound, which means unroll the loop up to some k, which means I make it flat almost. And then I can do so many nice things, right? Now, it is possible that when I unroll the loop 5 times, I can't catch the bug. But when I unroll it 6 times, I can catch the bug. That is possible. So the algorithm I'm going to talk about is one such under approximate algorithm, which is called dynamic partial order reduction, DPOR algorithms. If you search DPOR, there are a lot of references you will get. So I'm going to talk a bit about, even within DPOR, how do things work, a very high level overview, and some interesting theoretical problems even behind the development of the algorithm. Okay. Yep.
The justifications for working with TSO was also that if you want to only have sequential concurrency, then almost everything that you need to immediately go to the main memory.
Exactly.
Get sense to kind of buffer.
Absolutely.
What is the justification for RA?
So as I said, RA is the PL world's translation of the concurrency primitives inside a programming language. So now we have locks, right? Now lock is a concurrency primitive in C11's latest version.
What is that?
In the programming language itself. So, and I don't know, there are also these programming languages like Go and Rust and Kotlin, okay, where you have explicit, buffers between the processes. So in some sense, you can also think that many of these things have found their way into many of these latest programming languages. So answering some questions here will be relevant also to verifying programs under Go, under Kotlin, under Rust. Yeah.
Hardware happening in the PL world rather than the hardware release acquire.
Yeah.
Are there program languages which work already existing, which have released acquire, or still in a sort of a research stage?
So right now, my understanding is, so there is this RC11, RC20 programming languages. So of them, release acquire is a fragment, which means, the actual programming language is even more nasty. RA is still better behaved, even though it's undecidable. So you can understand. So the reason I'm telling you is, so if you think of full RC20, they have things called atomic and non-atomic accesses when you try to read and write. So these non-atomic accesses are very nasty because they can be racy. They can create races in the program. Whereas RA has only atomic accesses. That is why RA is better behaved amongst the lot. Okay, so, to try to, start thinking about how will you build such a tool, okay? So first of all, how am I going to track all the executions, right? That's the first question I must think about, right? To try to answer your question. So I am not going to, so for example, right, this is an execution. I am not going to think about an execution in this way. I am going to think of it as a graph. And the advantage of thinking about it as a graph is I can basically collapse several executions in one single graph. So it becomes like an equivalence class. I'll tell you how it's an equivalence class. So if I try to model this, okay, as a graph, so I'm first writing all the respective events, reads and writes. So what are the edges of the graph? There's a program order which is coming from the program directly. So I have to do nothing about it. So draw the PO edges. The next kind of edge that happens dynamically is the reads from, right? What value I choose to read from, what write I choose to read from is RF. And then there is a coherence order, the order in which writes happen to a same variable, right? If x1 happens and then x2 happens, then I will have this kind of CO edge between the two writes. And the last kind of edge I have is something called from reads. So what does a from read do? So notice that this guy has written, read from this value of x. Now this was the value of x which overrode this value of x. So the from read is basically from the read to that write which overrode the value it read from. Anyway, this is just a choice of edge, okay? Don't worry too much about why FR is there. Even if FR is not there, it's fine. Now, how do I check whether, so this is a very important problem I'm going to talk about. Now, in an actual tool I'm going to develop, I'm going to basically trace, this is called a trace by the way, okay? This graph is called a trace. I will be exploring traces and not actual executions, okay? Now, one question I have to ask is, so now, is this graph that I've drawn here, is it actually depicting a behavior under sequential consistency or not? If I'm talking about sequential consistency, let's say. How do I check that? Which means, is there a way for me to check that all the RFs I'm so-called drawing, are they actually reading from the latest value written? So the consistency check is very easy. So your graph at the moment is actually adhering to sequential consistency if this guy is acyclic. Okay? It's quite intuitive actually, because anytime you try to read from an obsolete value under sequential consistency, this FR edge here will create a cycle for you. Okay, that is why this kind of pretty intuitive. Now, this is not too hard to check, right? I just have to, cycle checking is not very costly operation, right? But okay, I need to put all the edges. That is the challenge here. So in any tool that you develop, one of the steps you have to check is the graph I have traced so far, is it basically adhering to my memory model? For sequential consistency, there's the condition. For other memory models, the conditions are going to be different. Obviously, right? Because they allow more behaviors. So maybe this kind of cycles are okay. For example, in RA, for example, I don't care if I have a cycle of this kind. I have some other condition which will tell me it is consistent under RA. Okay. Okay, just to kind of tell you that, these graphs are a better notation than the executions. So if you look at these two executions, they're two different executions, right? Do you agree that this graph captures both these executions? So what are the important information? PO is anyway fixed, right? Now the values read from are 2. And RF is basically capturing that information. It doesn't matter in which order I am, reading from. Right? So in that sense, I can basically associate with both these executions this single graph. So, okay, I have some. So in some sense, asking whether both these executions satisfy some property is equivalent to asking whether this graph is satisfying that property. Right? Because both executions are in agreement with this particular trace stuff. Okay, I'll quickly run through some examples to show that, okay, working with traces is better than working with executions. So look at the top guy here, 2 executions. This graph is corresponding to both these executions. Exactly. By trace, I always mean a graph like this, who has this RF, PO, and CO edges. Okay, that's what I mean by a trace. So clearly, I don't need to think of both executions, right? They're both captured by that single trace. Same here. So now comes an interesting point, okay? Now look at these two graphs. they're differing only with respect to the direction of the CO edge. Their PO, RF are exactly the same. So somehow, so now the question is, how many different traces should I explore before I can, completely say that I have looked at every possible execution? My job was to say that I have looked at every possible execution. I don't want to look at individual executions because they are far too many. So I'm trying to work with an equivalence class. So now by equivalence class, what I mean is, I am going to say two graphs are equivalent if they agree on their PO and RF and CO, but ideally if I can drop CO also, then the number of traces is even smaller to explore, right? So that's what I really want to do. So for sequential consistency, I cannot do that. I cannot drop the CO edge. I have to keep all three. But for the weaker models, especially for RA, I can actually drop the CO edge. I can just work with graphs which have the same PO and RF, which means a whole bunch of executions can be put into one trace with a certain PO RF edge. Another bunch of executions will be into another trace which has a different PO RF. PO is same, of course. RF is different. That's basically what it is. I want to ignore the CO edge. Because if I can do that, as you see, in some sense, I have even one less trace. Okay, in this example, I have only one less trace. In practical examples, it can be many, many more. So the structure of the algorithm is going to be, take a program as input, take the whatever assertion. Your algorithm should be one which basically explores only consistent traces. What I mean by consistent is, does it agree with your memory model? So think of some acyclicity condition, okay? We don't need to know what exactly it is. For SC, it is whatever I wrote. For RA, it is some other acyclicity. For TSO, it is some other acyclicity, but some such thing. But here, I am writing only different PO RF because I am already tuning myself into the RA mode. Okay. Clearly, what I wrote here is not correct for SC. For SC, I should say PO, RF, and CO, which means that many number of extra traces. Okay, so what should be the scheme of such an algorithm? Such an algorithm should basically ensure all the following. It's not obvious. Good question. So at least if you remember the kind of assertions I wrote, okay, they are all involving only local registers. Okay, and local registers are not connected by CO. The coherence order is only between the same shared variable, right? When I write x is 1 and then x is 2, I have a CO from x is 1 to x is 2. So if my assertion is only talking about local variables, then I can drop CO. It is fine. I mean, there is a bigger reason for RA, but in the interest of time and technical details, I think I'll just ignore it for the moment. So the things to think about is, okay, whatever your algorithm does, it must be sound, which means it must only explore those traces which respect your memory model. So this acyclicity check that I said, it must be done. There must be some way in which you can ensure that you have not left out a consistent trace. Right? Because if I do, then maybe there are some executions which are actually consistent. Maybe the bug is sitting there. And I didn't explore it, so I didn't know of the bug, right? The last thing is optimality. Can I ensure that every trace is explored exactly once? Okay, these are the three underlying important properties of the tool that you develop. How much more time can I take? 5 minutes is okay? No, I'll wrap up in 5, exactly, because I guess that's fine. 5 is okay. So I'm just going to ask you these two questions. Okay, so there are two different questions I'm writing here. One is a consistency checking, which says, given the program order, can you synthesize RF and CO so that the resultant graph respects your memory model? Okay, that's one kind of question. The second kind of question is what is called RF consistency checking, which means I am given both PO and RF. Can I synthesize CO so that the resultant graph is consistent? Now, clearly, this is an important step in my model checking algorithm, because if I can do these reasonably well, that's like one part of the algorithm taken care. So do we know how hard these questions are? That is the next thing I want to ask. So we know some answers. So for example, RF consistency is already NP complete for sequential consistency, and TSO it's in poly time for RA. So that's one reason for the weaker memory model. This works well. So remember, this is not a complete algorithm. This is an algorithm which is assuming that the loops are bounded. Full RA is undecidable, as I said. But as long as I'm willing to go with this under approximate analysis, where I say, okay, there was a loop, let me unroll it 5 times and run the algorithm. If I find the bug, awesome. If I don't, in the worst case, I will go to the boundary, right? I can't help it. So there are some papers which talk about, there are even recent works, as you can see, okay, which ask about these questions. So they're still kind of very relevant problems to work on. What I'll do in the next 4 minutes or 3 minutes, whatever it is, I'll show you a sketch of why this is NP complete for sequential consistency. I don't think I have time to talk about this polynomial time for RA. I have slides for that, but I'll not go through that and I will close. Okay. So how do we think of doing this NP completeness for sequential consistency? So my job is the following, right? I'm going to take some well-known NP complete problem. Let's say 3 SAT. Everybody knows 3 SAT, right? And I'm going to write down a program, okay, such that whenever the given formula is satisfiable, then I'll be able to find a consistent execution here. Remember RF consistency. So the program I'm writing must be one where even the RF edges are unambiguously decided. Remember, when I say RF consistency, I'm given PO and I'm given RF. My job is only to synthesize CO. Okay, such that I have a consistent execution. So the program I write must be one where I have no confusion to read from. If I'm trying to read A, okay, there is only one guy who's writing A. Then the RF is clear, right? If there are 10 people writing to A, I don't know, right? What do we mean by fixing RF? It's not fixed. Okay, so here is such a reduction. So I've taken just a simple formula here. Okay, there are 2 variables, V1 and V2. And the idea generally is to kind of write processes. So if you look at the way this has to be executed, so I have some processes which is trying to assign values to my variables. So I've shared variables V1 corresponding to the variable V1 in the formulae. Shared variable V2 corresponding to the variable V2 in the formulae. I have some extra shared variables like X is an extra shared variable, okay, which I need in my program construction. And then I have to now reason that, okay, if I can kind of find a consistent execution of this, then the formula is satisfiable and conversely. And I have to kind of also find, okay, what is the execution, okay, which basically is consistent. That's not hard here. We can just run through it. So clearly, right, a satisfying assignment is V1 is true and V2 is false. That will work, right? So if you notice, I have a process which assigns V1 true. I have another process which assigns V1 false also. Okay. So basically, I have as many processes per variable. So I have both here, but this is what I want here. So I can always choose to execute. So everything you see here is a process. Okay, I've just chosen the name so that this is kind of trying to give a value to my variable. And these are things which are going to check if the clauses are going to be true. Okay, the C stands for clause. Okay, so if I just try to run this first, okay, then I know V1 is true. I've assigned V1 is true. Then I'm trying to execute this program, this particular process, so that V2 is false. And now I'm trying to see, okay, can I make the first clause true? I'm going to read from V1. This assume statement is like a conditional check. Okay, I'm going to check if it is value is true. And then I'm writing to some other variable the value true. Okay, I have some way to ensure that the first clause actually is satisfied. Okay, so if I complete executing this guy, I know the first clause is true. Likewise, I'm going to do for the second clause. Okay, I'm going to read from V2. It must be false. Just clause is just single variable. And then I have something which tells me that, okay, the clause is actually satisfied. Now, remember, right, I'm trying to execute the whole program. So I have other processes which I have never run at all, okay, because of the choice of what I have. So I have to choose an order so that everything is executed and I'm consistent. So if you come to this guy now, so here at this point, it will basically write X is 0. Ignore this right for the moment. And then it is going to ensure that the first clause is true. And now the second clause is true. And now it is going to kind of, try to see if the remaining can be run. So now it is going to execute x is 1 here at this point of time. Then it is going to go here and say that, okay, I can read 1 from x. And indeed, I had assigned true to v1 as part of my satisfying assignment. And then it is going to do the same thing with respect to the second clause. And then just to finish my execution, I am going to run the rest in parallel. It doesn't matter, okay, because I know my clauses are fulfilled. So here I'll just run them in this order and I'm done. So I just want you to reflect on one thing before we close, okay? Why will this reduction not work for release acquire? If you take the same program and try to interpret it under release acquire, I'll give you a hint of where it will fail, okay? At least you'll agree with me that under sequential consistency, if I write this followed by if I write this, v1 can have only one value, right? I can't have both true and false. So imagine, right, if my starting formula was something of the kind v1 and not v1. Suppose that was my formula given. It's clearly unsatisfiable. So clearly, if it is unsatisfiable, then I should not be able to find a sequential consistent execution of my program. Under release acquire, the danger is the following. Now, here I can say v1 is true. This another write by another process which says v1 is false. Because they are both out there in the world, this guy can happily read, okay, v1 is true and say that, hey, clause 1 is true. Now, there will be a similar guy who would have said v1 is false. That guy could have read that and said happily clause 2 is true also. Which means under RA, there are more behaviors possible, which means I could have still found a consistent execution here when the starting formula was unsatisfiable. I know this is not a very in-depth description of why under RA this won't work, but just to kind of give an intuitive feel of why under RA this is a problem. Under RA the problem is in poly time, so clearly it better not work, let the reduction not work, okay? I guess I will stop here running through the rest of the slides, which is trying to tell you why it is easy in RA, okay? The RF consistency, why it is very easy in RA, why it is under poly time. So what I should do, I should go to the last slide because it doesn't help to just show the slides now. Why am I stuck? Okay, it's stuck. But anyway, the message I wanted to pass is basically that, so we do have algorithms and tools for, some of these well-known memory models, but clearly an efficient consistency checking is still very much under investigation. So if you're theoretically inclined, there are other things which you can do also. Like for example, I said it's NP complete for SC. Maybe you can ask, okay, can I have finer bounds, right? This W1 class, stuff like that. It is still useful to know. I can ask other kind of questions. Suppose I fix the number of threads, number of variables. Can I hope to do better? Or suppose I say that, there are only 2 writes per variable in every process I have. Then does the complexity become better? Right? There are so many directions you can think of if you are theoretically inclined. Tool development, of course, is part of this work. Then there are parameterized versions of this problem, right? So here I'm assuming I have fixed number of processes. But there is also this parameterized kind of concurrent programs where I do not know a priori the number of processes given to me. Then what happens to all these questions? So basically what I want to say is that, okay, this is a very upcoming young area where a lot of, theoretical insights will help apart from tool building. And if you can help in building efficient algorithms, then that will translate to efficient model checkers and therefore to verification of the concurrent program. I hope I answered your question. Did I? Somewhat, yes, I know. I wish we could go into more detail, but at least it's better than what it was, right? Okay. Okay, so I'll close. Thank you so much and sorry for taking extra time.
So you have put in approximation schemes for these.
Yes, yes. So for release acquire, there is a very good under approximation known. That's a different talk. Yes, I can share some resources. I can send to Mrinal or Ramprasad. Absolutely. Yeah.
So the newer programming languages, they have these borrow checkers that's supposed to make sure that, to try and make it programmers to write bad code.
Yeah.
So for example, use of borrow checker sort of a thing, does that fit into any of this? Those don't involve transferability, but it's just like sort of good programming practices that you.
Yeah. So I don't know the answer for that. So all that I know is that, like in this UPSLA, it's a conference. There's a paper which got accepted, which is having a tool called MUST. Model checker for Rust is MUST. I'm supposed to read that paper. I don't know. But all that I know is that people are actively trying to answer these questions for these, whatever, more fashionable languages. And we are trying to catch up. Yeah.
Be complete. And that we know that the fat solvers are typically.
Yeah.
Very instances.
Yes.
That word SAT is considered an easy problem.
Sure.
So are there things in which out here the first thing you do, you transfer them and use those SAT solvers and actually you have a completely feasible.
Yeah. So actually, if you look at the deeper algorithm for sequential consistency, it invariably invokes a SAT solver. It does. And kind of, it's not something we like very much, but it has to be done for SC because it's hard anyway. But for RA, obviously, we don't need to do such things. So yeah, that balance is always there, that question. The algorithm does invoke a SAT solver at the backend.